All right. Welcome to the F-Star pop-up seminar. This week we have Cezar Andrici from NPI, who's going to tell us about securing verified I/O programs against unverified code in F-Star. Thank you, Cezar. Take it away.
Yeah, okay. Thank you very much. Yeah, thank you for having me. So my name is Cezar Andrici, and this is joint work with some amazing people. Some of them are in the audience, some of them are part of F-Star community. And we just submitted this to Popl. So today I'll talk about how to secure verified I/O programs against unverified code. And give me a second. Okay. So we use F-Star and other proof-oriented languages because they give us strong guarantees. Let's take a simple example, like we try to verify a web server, and we want to verify that this web server satisfies a specification such as that it responds to every request. So what we do in F-Star is that we take this specification and we encode it in either refinement types, or we annotate functions with pre and post conditions. And F-Star will help us and it will verify that the code satisfies these pre and post conditions. And if the verification is successful, then we have a strong guarantee that the web server responds to every request. So this is great. And for these strong guarantees, there is an increasing number of verified realistic applications. These are some examples, some done in F-Star, some done in Coq. What they have in common is that it took a lot of effort to verify them. And I mean, it was worth it for the strong guarantees, but we would like to speed up the process. And usually what happens is that one would like to use existing libraries. And here by existing libraries, I mean unverified libraries. However, if one tries to add an unverified library into their code base, to finish verification, one has to make some assumptions about this code. Of course, one could verify the library, but what would be the point of verifying? I mean, it will not speed up development. So the problem here is that now we have these assumptions, and there is no guarantee that the library satisfies the assumptions. And this is unsound and, of course, insecure, especially if this library is buggy or it's adversarial. It can steal secrets or install malicious code. So basically, we lost our strong guarantees in this case if we do this. So the alternative is to convert these assumptions into dynamic checks and to do this in a verified manner such that we preserve our strong guarantees. So in this work, we propose a secure compilation framework that dynamically enforces the assumed specification. So we have the verified program, let's say our web server. We have an unverified library. What we do is that we use two techniques. One of them is higher order contracts. So during compilation, we add higher order contracts. Higher order contracts will wrap each function of the web server into a new function that will enforce things like refinements, such that a number should be positive, or preconditions, such that the file descriptor has to be open. However, higher order contracts are not enough. Some specifications have to be enforced by prevention. For example, if we want to say that the library should not open some secret file, we have to prevent the library to open a specific file. So for this, during linking, we add a reference monitor, and this reference monitor will enforce an access control policy before each operation. And it will block the library, for example, to open secret files. So the resulting application of this will be an application where the web server and the library communicate through higher order contracts, and where the reference monitor watches the operations done by the web server and the library. It will keep track of this in its internal state, and it will use this state to enforce the access control policy only on the library. One important thing is that the higher order contracts have access to the state. For example, if the higher order contract enforce the precondition such that the file descriptor passed as argument must be open, the higher order contracts looks in the state of the monitor to see if this file descriptor was actually opened or closed in the meantime. Right. And because we proved the soundness theorem about our framework, we also have that this resulting application actually satisfies the specification we want, that it responds to every request. So we have our strong guarantee that this program responds to every request. We do not lose it, even if we linked a verified program with an unverified library. So that was the high-level picture. In this work, we managed to do this for terminating IO programs. And here by IO, we mean the effect IO, in the sense that we can read and like open file descriptors, close them, read from them, open sockets. We plan to add other effects such as non-termination, state, and exceptions in future work. And the contributions of this work is also that we introduce an actual way to verify terminating. Okay, Nick, do you have questions?
I was just wondering about this, the example property you gave, like response to every request. Is it just a straw man example, or is it, I mean, because it sounds like a liveness property. Is that something that you are actually enforcing?
Well, yes. Well, it is a liveness property if the web server is non-terminating. Because our web server is terminating, it becomes a safety property.
I see, because it's terminated. And this works even in the presence of an unverified, well, potentially buggy library that could, the library itself might loop, right?
Right. So our assumption for now, is that the library is not in some, it is also terminating, in the sense that our target language is a safe subset of F star that only allows terminating IO programs.
I see. And if the library misbehaves, the server might still respond, but it might respond with error or something.
So yes, if the library misbehaves, the higher order contracts or the reference monitor will return an error to the web server. Mm-hmm. And the web server handles that and responds to the client.
All right, makes sense. Thank you.
Okay. Okay, so so the contributions. The first is how to verify terminating IO programs. We build on Dextra monads, the paper Dextra monads for all. And here we present an effect that allows us to verify our programs. We also present our compilation framework, which systematically converts assumptions into dynamic checks. And by systematic, we mean that sometimes, even if we leverage type class automation and SMT automation, some specifications are not executable, and we cannot automatically convert them to dynamic checks. So the framework will ask for the dynamic checks. The good news is that it requires only the checks that are actually needed, and it also verifies that these dynamic checks imply the assumptions. So one cannot provide dynamic checks that will break the assumption or not imply the assumption. And the first thing is that we actually show that our framework is secure because we prove a soundness theorem in F star, and also one of the strongest secure compilation criterion, robust relation hyperproperty preservation. So let's look at how to verify terminating IO program. This is a very simple example. There are more in the paper. So here it's a function prog that takes as argument another function called read contents. And the body of the program is simple. It opens the file data.csv. It takes the file descriptor and it passes it to read contents, and then it closes the file descriptor. So this is very simple. What's more interesting is the type of this function prog. It's in the effect MIO, which stands for monitored IO. This is our own effect that allows us to verify IO code. Here, it allows us to write a precondition over history. So these are histories. Histories are traces that happened in the past before calling this function. And then a postcondition over the history, the result, in this case is unit, and the local trace. So the local trace are the events that produced during the execution of this function. And here the postcondition says that the file ethical password was not open. Right. So this is a very simple postcondition. And we can look at the local trace. So the local trace will have the structure where for each IO operation, there will be an event associated with it that will contain the arguments and the result of each operation. And we have an event for open file, an event for close. And of course, we need some events for the read contents, but we don't know yet what read contents does. And here, I mean, let's assume that read contents is our unverified program that we would like to pass to this verified piece of code. And here it should be like an arrow from a file descriptor to a string without any pre and post conditions. But of course, we cannot give this type to the argument read contents. And we cannot do this because we will not be able to finish the verification, because read contents could open the file at password. We don't know what it does. The specification is too weak and it will allow the attack. So we cannot give such a weak type to this argument, and we have to give it a strong type. And by strong type, we mean a type that has pre and post conditions and refinement types. And here, an example is we can give it a precondition that the file descriptor given as argument is open, right? We can also, the type of read contents can have as a post condition that the result must be read from the file descriptor given as argument, right? I mean, this is expected from a function called read contents. It should return the contents of a file. And also we have option to give it a post condition that describes the IO behavior, which should be in our case that it doesn't open at password. And this post condition will be enough to verify our program. So this strong type has 3 types of specification for us. The precondition and the first post condition can be enforced using higher order contracts because they can be checked, or they don't have to be checked, the precondition, but they can be checked either before calling read contents or after read contents returns. But then this post condition that it doesn't open at the password, we have to prevent this. And this would be our access control policy that the reference monitor enforces on this code on each IO operation to prevent read contents from calling, from opening this file. Okay. So the verified web server or our program uses this. Okay, Nick.
Sorry, Cezar, but it took me a while to unmute. If you can go back to the previous slide. You were saying this, the post condition can be enforced simply by checking the result rather than needing the reference monitor. But here, this is some kind of a information flow or a provenance property, right? You're saying the return string is read from FD. Like, how do you enforce that?
So the monitor will keep in its state that it's read from a file descriptor some message, right? And when we enforce the post condition, we can look at what this function read from that file descriptor and check maybe if the concatenation of those contents equals to the string. I mean, so we don't necessarily require, but it's easy to think that the monitor state is the trace. So each time this function will read from this file descriptor, will produce an event that actually has also the result on the trace. So it will be very informative. And then one just looks at the trace and checks for all read events on that file descriptor, what were the result, and then check equality.
I see. Okay, I think I understand. Thanks.
Okay. Are there any other questions? Okay. Right. So our verified program or web server uses these strong types, but our unverified library or our read contents function that is unverified should have a weak type, meaning no precondition and no postcondition. And we have to bridge the gap between these two. And we do this using the two techniques. And we have an intermediate point, which we call an intermediate type. And basically, we have to bring the strong type to the intermediate type and the weak type to the intermediate type. And during compilation, basically, the web server, so the source web server expects a library of a strong type that contains assumptions. After compilation, it will expect a library that has an intermediate type that has less assumptions. And the reference monitor will add some specs to this weak type. And let's see how. So this is only looking at the types. So for the first step, we have, this is a general type that has refinements, it has pre and post conditions. And we would like to bring this type to intermediate type, where there are no refinements, no preconditions, and the post condition is only the access control policy. Remember, because the higher order contracts do not take care of the access control policy in our case. And we do this by using a mechanism that implements a function, two functions, export and import. And what they do is that for here, to go to an intermediate type, this strong type will be exported. It will be wrapped into a new function, and where the precondition and the refinements are enforced dynamically. And then on recursively, it will call import. And this is to support higher order types. Asim, do you have a question?
Yeah, so I was wondering, like, so are the two kind of things separate? So you said the check that only the contents from FD are read is done in the higher order contract, and the access control check is done in the monitor.
Yes.
So as I understood from the previous question from Nick, like even for the first one, where you check that the FD, only the FD is read, you're kind of peeking into the state maintained by the monitor to say that what are the read events issued by the library, and you concatenate those strings to see that that's the output it's returning. So yes. Why can't we do the access control check same way, like monitor will maintain in its state also what are the FDs that the library has opened. And we could go and check that it hasn't opened, for example, etc password FD, and do it there rather than somewhere else.
Right. Good question. It is because it will be too late to check at the end of a function that it open ethical password. By the time we check, the function could open ethical passwords, read the contents, deliver them over the network, right? And by the time we see at the end of the function that the read contents did this, the property will be broken.
Got it. Got it. So the second kind of the reference monitor, the true reference monitor checks are like then and there. As soon as it tries to open, it's going to get a failure.
Exactly. Yes.
Got it. Got it. Thanks.
Okay. Right. Yeah, so for this export and import, they are implemented using type classes, are part of our compilation framework, and they are used during compilation automatically. And yeah, they are defined in terms of in terms of the other to support higher order types. So here it's like a first order type, but we support higher order types. For the second part, for going from a weak type to an intermediate type, we just give intuition here because the actual type of a weak type is using epoch polymorphism, and it's hard to explain. What the important intuition here is that the weak type doesn't have its own specification. It doesn't have a precondition and a postcondition. We don't know anything about this code except that it goes from A to B and it's not effect. And what the reference monitor does is that it enforces the access control policy on pi. It enforces the access control policy pi on a weak type, on something of a weak type. And the intuition behind this is very simple. If we link if we have a function and we prevent it from opening, for example, ethical password, we can say about that function together with the reference monitor that it doesn't open ethical password, right? So by enforcing this access control policy on a weakly typed function, it gives us this intermediate type function. Okay. Oops. Okay. So about our compilation framework, we prove that it's secure, and we do this in F***. We have a mechanized proof of soundness, and also one of the strongest criterion. In this presentation, I only show that the setting where the program uses the unverified code as a library, but we also support the other case, and we prove for both cases that these two settings hold, these two theorems hold, soundness and robust relation hyperproperty preservation. And here I would only like to talk a bit about robust relation hyperproperty preservation. So I said that it's a strong criterion presented by Abbott et al. And what it gives us is that if the source program satisfies in the source language any relational hyperproperty or any property, then compilation preserves that property into the target language. So this is a very strong criterion. And what's interesting in our work is that the proof is by construction, and it's actually very simple for PSNT. And this is because our source and target languages are shallow embedded in F-star. And we use, as I said, effect polymorphism, a variant of effect polymorphism, which we call flag-based effect polymorphism. And we also designed our hardware mechanism, the import and export function, such that we can do this easily. There are more details in the paper, like how we defined our effects and how to, how do we define our effect. Our effect is engineered to work well with SMT. We can actually verify good amounts of code with it without using too many tactics or lemmas. As I said, the code is verified and we have mechanized proofs. And we also have a case study of a web server. This web server actually accepts multiple clients and it responds to each request. And the thing is that the request handler is actually unverified. And we still show that the web server responds to each request and that the web server is safe against some adversarial handlers, but we also show that it works with a proper handler. So maybe I'll give you also some details about the future work. Right now, our languages are in F-star and are subsets of F-star. The first thing we would like to do is to extend with non-termination here with state and exceptions, and maybe have like an effect that can do all four of them and be able to verify code using it. But in parallel or orthogonal to this, we want to extend this to OCaml. And we actually right now recently managed to take a deep embedding of STLC and show that we can translate unverified program in STLC to our model of unverified code, and that our secure compilation theorems solve. But still, this is work in progress and it's more to go. Yeah, so I'm open to questions now, and I have more slides if you have specific details or specific questions.
Yeah, maybe I can kick it off. So I want to ask about the RHP stuff. So, the basic question I have is like RHP is usually described as like for all adversary context that exists as source context, right?
Yeah.
So that's one thing, and then the other one is like, so this MIO monad is like a, pre and post conditions on a single trace, right? So I assume somehow you're relying on some like parametric property of F-star to guarantee the existence of the source context. Is this what's happening?
No.
Actually, can I interrupt? Can I ask an even more basic question? Can you do you have a definition of this RHP property somewhere?
Yes. I told you that I have slides.
Mm-hmm.
Yeah, so this is I think the property free characterization, which we prove in F-star. So what it says is that for all target contexts, like unverified code, exists a source context such that for all programs, the behavior in the target is equal with the behavior in the source. Does this definition sound familiar? Yeah. And to prove such a criterion, one has to define here a back translation to give a witness to this existential. And actually, I will. Did the share screen stop?
Yes.
Okay,
Yeah, we see.
Yeah, I wanted to jump quicker from. So we actually are able to define a back translation by composing this step of.
Actually, I don't see any. I don't know if others see something. I just have.
Yeah, I just see a blank screen.
Yeah.
It's blank for me too.
Does it work now?
No.
Does it work now? Now it's the entire screen.
Yeah, we see.
Yeah, that's fine.
Okay, so what I was saying is that to prove the RHP or the robust relational hyperproperty preservation, one has to define back translation, and we actually can define back translation by composing this translation from a weak type to an intermediate type, and then with import, right? So we can go from a unverified code to a very strongly typed context just by composing these two. And yeah,
So
and
is this?
for us,
Oh, sorry.
yeah, okay. I wanted to say that for us is very easy to prove because we actually can prove even something more strong. We can prove this syntactic equality, where, yeah, I mean, it's not, we don't have to show any behavior. We show that the whole programs are equal syntactically.
And you're working in a shallow embedding, right? This is just an effect in F star.
Yes.
How do you describe like quantification of a context?
Okay. So we use type classes to restrict. We use type classes to restrict what is an intermediate type. So we define our intermediate types as arrows that have as a post condition and access control policy.
Or maybe I don't know if you have code easily accessible, but are you able to show us what the statement of your theorem looks like in F star?
Yes, but I mean, this is an F star crowd, so maybe it will be easy to understand. So can you see my code?
Mm-hmm.
Right. So this is the file where the verified program takes the context as a library. And to state the theorem, we have to think that the program and the context communicate through an interface. But the interface is just a type in our case because we use functions. So our source interface contains the type of the context. And this is the flag for flag polymorphism. So our context is just a type. But we say that our source context has to be importable. And what this means is that, again, as I said, we only define our intermediate type. And our strong types are types from which we can import and export to. So we don't have to give a concrete definition. And then for weak types, we have something different. But so here, yeah, we make sure that our context is of a type that we can import or export by using this type class. And then we have the target interface that again has this only the type of the context that is flag polymorphic, and then the fact that, so you can see here, so the type of the context here of the target context that is unverified is still an intermediate type, but it is flag polymorphic, which for us is a form of effect polymorphism, and we show that this characterization of the target context is enough to encode any unverified context. Yeah, I don't think this is easier. Yes, Asim?
So can you please remind me what the flag was? Sorry, I forgot.
Yeah, so I did not present the flag. So the flag in our effect is another index that allows us to restrict what operations a computation can do. And it can have 4 values. I think I have a slide. Like no operations, only IO operations, or I mean, these are the values. So basically, by making this flag, making a computation flag parametric, we make that computation unable to use any of the operations of the effect. Right. So yeah, if we look at our target context, so the type of our target context is here. So it is flag polymorphic. So the context by itself cannot call any operations anymore now. But we pass our own operations that come with the monitor and enforce an access control policy. And because the context can only call into these operations that we provide, and we know that they enforce the access control policy, the context inherits this specification. And we can show that the context initialized with these operations that have the monitor satisfy the access control policy.
So is that some meta argument based on parametricity of this flag, or you're able to prove it in some way?
It is a meta argument.
Is it really a meta? I was actually thinking you would say it's not, in fact, a meta argument, because you're not type parametric here. The flag is some concrete thing, and you can prove that if your effect is parametric in this flag, it can't use any concrete operation.
So I think Exe and Guido worked on this, and they can tell you more about this. I think the problem was that erased is a close. We use erased here, and we cannot, where the erased doesn't have a formal specification, and we cannot reason about it. Guido, can you?
Yeah. So yeah, we try to do this proof. So like the idea is just that, right? If it's parametric on the flag, it cannot expect it, and therefore it cannot do anything that requires a particular flag. Mm-hmm. But proving that requires to assume parametricity for functions of this type, right? So you would have that axiom at least.
Yeah, so I mean, even if this was not erased, I don't see how would you formalize this property without?
I think you need to assume that the function is parametric in this type, and then you can prove it. Then you can prove that. The idea is that since the flag is erased, we were hoping to be able to say any two flags are related, so they need to be. So you cannot really expect it, and even if you change it, the results are going to be related, so you wouldn't observe a difference. But yeah, we couldn't really get a decent property to work there. It's not that that clear, we could just take the like a universal relation between flags, because we need to use it in types which are ghosts, so then you can inspect it in the types. Yeah, so we don't have like a fully end-to-end thing. But even if we sorted it out, I think you still need to assume that the program is parametric, and if you assume that, then I think it might be possible that we give a proof that it does not inspect the flag and it behaves properly. But, yeah.
Yeah, so to make, I mean, we did not manage to make this proof, but like to make this meta argument stronger, what we did is that we have a deep embedding of STLC, and we have a translation from STLC to context of these types. And this is, yeah, just to make our meta argument stronger, but we thought about a proof for this, or at least how to state a theorem about it.
Can you show us the theorem?
What theorem?
Like, is there a main theorem?
For RRHP, or like for the robust relational hyperproperty, or?
Yeah, show
Okay.
your wrappers give you RRHP.
Okay, so maybe. So what we actually did here is that we took the model of I mean, this is the, okay. So we took the model from a paper of Catalin, Beyond the Full Abstraction. And there they define a compiler where the source language and the target language are defined using some interfaces and some relation between traces in the source and traces in the target. So we define this file by translating it from Coq to star, and then we just instantiated it with our model. So, I mean, this is the theorem that I showed you on the screen on the slide, right? Is for all target contexts exists a source context such that for all source program, there is a relation between the behavior in the source and behavior in the target. I can show you that the proof is easy of this. I mean, so we instantiate this model, as I said. So for our soundness theorem, yeah, the SMT can prove it automatically. And then to prove robust relational hyperproperty, as I said, we can prove actually a syntactic equality between the whole target program and the compilation of the whole source, the source whole program. So because we can prove the syntactic equality automatically using the SMT, then it's, well, here we just play with to convince F star, but the proofs are very easy. Like it's just one line of code until we can just prove it.
Cool. I'm surprised you get syntactic equality. Is there some intuition for why you get something so strong?
It is because we use the MIO effect in both source and target, right? And we only restrict what are the specifications that can appear in the source and the target. And even if the specifications are erased, like they are not intrinsic anymore, they're not part of the type of the source program, we are able to keep them around as extrinsic properties and use them in the final proof.
So when you go from STLC to these source MIO programs. This syntactic equality theorem will not hold, right? Because you're not comparing two MIO programs, you're comparing an MIO program to some other kind of representation, right?
Right. I mean, so the STLC like not experiment, but argument is that we are able to go from an unverified program in STLC to our target context, right? And because we actually obtain something of that target context of that type, our proofs just hold.
Yeah, I mean, in essence, you have to prove that your compilation from STLC to unverified MIO is RHP as well, right?
Can you repeat that, please?
Well, because RHP is transitive, so
so we don't prove RHP at the level of STLC, right?
sure.
We just show that our weak types are not the representation is correct. If I go back to the slide, extending RHP and soundness to this layer is still future work, right? We did not manage to do compilation to STLC. This is something that they try to do for Coq with the CertiCoq project, right? We only managed to define this error here, okay? And our hope is that somehow we will manage to maybe port some of what was done in CertiCoq and finalize this part too. But yeah, for now, we need a strong argument that our weak types are actually weak and don't have specification.
That makes sense. Thank you.
Any more questions? I have a question just on kind of related work. Is anyone else doing this kind of proofs of relational hyperproperty preservation on programs with IO?
For programs with IO, I don't think so. There are some works on state. Yeah, I mean, for IO, I think it's we are the first ones.
And is anyone doing this RHP kind of stuff on like on actual programs, not just like the calculus?
This actually I don't know. I mean, I think there are many, well, not many, but I think there are works that try to prove RHP about compilers, but usually those are done with deep embeddings, and are very hard proofs that take a lot of space, and usually they are manual, right? So yeah, I mean, for us, everything is easier because of our shallow embeddings. And yeah, we also tweaked our designs and our representations such that they're intuitive and easy to work with. It took a long time to find them. Yeah.
Sambit had a question in the chat. He says, hi Cezar, thanks for the great talk. I had a question. How does your reference monitor interact with access control policies defined by the OS itself? Say you want to read from etc password without any explicit postcondition specifying this, but the OS doesn't grant permission to read it. Would that just be an exception raised by the IO library?
Right. So all our operations can return are sums of a value or an error. We don't really support exceptions now, but all of our operations return an error. So we can return an error. So if the OS blocks the operation, then it will be an error. And we can distinguish between them because we have special codes for the errors of our reference monitor.
Any last question? Comment? Oh, well, thanks, Cezar. That was really interesting. Sounds super cool. I'm looking forward to reading more about it. And is there a pointer to the code somewhere?
To the code, yes, there is the
Can you maybe paste it in the chat or something? Oh, there you go. All right.
okay.
All right, that's great.
Okay.
All right. Thank you so much.
Thank
Thank
you.
you.
Thank you.
Bye.